StatQuest is on my mind all night long. StatQuest. Hello, I'm Josh Starmer and welcome to StatQuest. Today we're going to talk about odds ratios and log odds ratios, and they're going to be clearly explained. The StatQuest on odds and the log of the odds ended in a cliffhanger. We talked about how the odds are just the ratio of something happening, i.e., my team winning, to something not happening, i.e., my team not winning. We illustrated this with circles. Blue circles represented my team winning. Red circles represented my team losing. And the odds of my team winning were just the blue circles over the red circles. Alternatively, we could just use numbers to represent the odds. And when we do the math, we see the odds of winning are 0.5. The cliffhanger came when I said that even though the odds are a ratio, it's not what people mean when they say odds ratio. So let's clear this up once and for all. When people say odds ratio, they're talking about a ratio of odds. So we've got a ratio of these odds to these odds. Doing the math gives us 2 divided by 4 over 3 divided by 1. And that gives us 0.17. Just like when we calculate the odds of something, if the denominator is larger than the numerator, the odds ratio will go from 0 to 1. And if the numerator is larger than the denominator, then the odds ratio will go from 1 to infinity and beyond. And just like the odds, taking the log of the odds ratio makes things nice and symmetrical. For example, if the odds ratio is 2 divided by 4 over 3 divided by 1, then the log of the odds ratio equals negative 1.79. And if the odds ratio is the opposite, it's 3 to 1 over 2 to 4, then the log of the odds ratio is the positive version. It equals 1.79. Great! Now that we've got that cleared up, what can we do with odds ratios? Here's an example of the odds ratio in action. We've got a bunch of people, 356 to be exact. 29 of these people have cancer, and 327 do not. We also know that 140 of these people have the mutated gene. I'm just going to let you imagine which gene I'm talking about here. And 216 people do not have the mutated gene. We can use an odds ratio to determine if there's a relationship between the mutated gene and cancer. If someone has the mutated gene, are the odds higher that they will get cancer? Given that a person has the mutated gene, the odds that they have cancer are 23 to 117. So we'll put that on top of the odds ratio. And given that a person does not have the mutated gene, the odds that they have cancer are 6 to 210. So we'll put that on the bottom of the odds ratio. Here's our odds ratio. We do the math, and the odds ratio tells us that the odds are 6.88 times greater that someone with the mutated gene will also have cancer. And the log of the odds ratio is 1.93. Small bam. What does all this mean? The odds ratio and the log of the odds ratio are like r squared. They indicate a relationship between two things. In this case, a relationship between the mutated gene and cancer. And just like r squared, the values correspond to effect size. Larger values mean the mutated gene is a good predictor of cancer. Smaller values mean that the mutated gene is not a good predictor of cancer. Bam! However, just like r squared, we need to know if this relationship is statistically significant. So let's do it. There are three ways to determine if an odds ratio, or log of an odds ratio, is statistically significant. 1. Fisher's exact test. 2. A chi-square test. And 3. The Wald test. One super annoying thing is that there is no general consensus on which method is best, and people often mix and match. Some people will use Fisher's exact test or the chi-square test to calculate a p-value, and use the Wald test to calculate a confidence interval. And some people are happy to let Wald do all the work, calculate the p-value and the confidence interval. The last method ensures that the p-value and confidence interval will always be consistent, but check and see what other folks do in your field to find out what is most acceptable. So let's start with Fisher's exact test. Step 1. Watch the StatQuest on enrichment analysis using Fisher's exact test and the hypergeometric distribution. Bam! Now think of the people as a bag of tasty M&Ms. People with cancer are represented by 23 plus 6 equals 29 red M&Ms. People without cancer are represented by 117 plus 210 equals 327 blue M&Ms. Now, just like in that StatQuest, we work out the p-value for grabbing a handful of 23 red M&Ms and 117 blue M&Ms. And just like in that StatQuest, we use a computer and it says the p-value equals 0.00001. Another small bam. Now let's talk about how to calculate the p-value using a chi-square test. The chi-square test compares the observed values to expected values that assume there is no relationship between the mutated gene and cancer. To do this, we calculate the probability of having cancer as the total number of people with cancer. That's 29. Divided by the total number of people. That's 356. So the probability of having cancer is 0.08. So if the gene is not associated with the 23 plus 117 equals 140 people with the mutated gene, then the probability of having cancer times the number of people with the mutated gene equals 11.2. Thus, the expected number of people with the mutated gene and cancer is 11.2. And the remaining 128.8 people with the mutated gene are expected not to have cancer. Likewise, if the gene is not associated with the 6 plus 210 equals 216 people without the mutated gene, then the probability of having cancer times the number of people without the mutated gene equals 17.3. Thus, the expected number of people with cancer that do not have the mutated gene is 17.3. And the remaining 198.7 people with the mutated gene are expected not to have cancer. Now we do a chi-square test to compare the observed and expected values. And the p-value is 0.00001 with the continuity correction, and 0.000004 without the continuity correction. If you're not familiar with the chi-square test, don't panic. We'll do a StatQuest on it. One last small bam. Lastly, let's talk about the Wald test. This test is commonly used to determine the significance of odds ratios in logistic regression and to calculate confidence intervals. The Wald test takes advantage of the fact that the log of the odds ratios, just like the log of the odds, are normally distributed. This is a histogram of 10,000 randomly generated log of the odds ratios that tells us what to expect if there is no relationship between the mutated gene and cancer. Psst. If you want to draw this histogram at home, randomly pick a total number of people between 300 and 400. We do this to simulate the fact that if we repeated this experiment, we might not get the exact same sample size each time. Then, for each sample, select a random number between 0 and 1. If the number was less than 0.08, the proportion of people with cancer, then the sample has cancer. Then, pick another random number between 0 and 1. If the number was less than 0.39, the proportion of people with the mutated gene, then it has the mutated gene. This gives you a matrix of random values that did not depend on a relationship between the mutated gene and cancer. Lastly, calculate the log of the odds ratio. Do this 10,000 times and draw a histogram. A normal curve fits pretty well. Notice that the histogram and curve are centered on 0. When there is no difference in the odds, the log of the odds ratio equals 0. The standard deviation of the 10,000 log of the odds ratios is 0.43. However, it is more common to estimate the standard deviation from the observed values. You do this by taking the square root of the sum of 1 over each of the observed values. If we do the math, we get 0.47. The two different standard deviations that we calculated are very similar. All that the Wald test does is look to see how many standard deviations the observed log of the odds ratio is from 0. And since the Wald test typically uses the estimated standard deviation, we'll replace the histogram with a normal curve centered on 0 that has a standard deviation of 0.47. The log of the odds ratio is the same one that we already calculated. Here's where the log of the odds ratio goes on the curve. To find out how many standard deviations the log of the odds ratio is away from 0, we simply divide by the standard deviation. Thus, we divide 1.93 by 0.47. And that gives us 4.11. So our log of the odds ratio is 4.11 standard deviations away from the mean of the distribution. A general rule of thumb with normal distributions is that anything further than 2 standard deviations from the mean will have a p-value less than 0.05, so we know our log of the odds ratio is statistically significant. However, to get a precise two-sided p-value, we can add up the areas under the curve for points greater than 1.93 and for points less than negative 1.93. However, this is traditionally done using a standard normal curve, i.e., a normal curve with mean equals 0 and standard deviation equal to 1. And that means adding up the areas under the curve for points that are greater than 4.11 and for points that are less than negative 4.11, where 4.11 is the number of standard deviations that the log of the odds ratio is away from the mean. Ultimately, the p-value that the mutated gene does not have a relationship with cancer is 0.00005. Double bam! Before we go, here are some final thoughts about the 3 different statistical tests we can use with the log of the odds ratio. When I generated the 10,000 random log of the odds ratios, I performed all 3 tests on them. If the tests worked as expected, 5% should have p-values less than 0.5. Here's what I got. For Fisher's exact test, 4% of the p-values were less than 0.05. For the chi-square test, with the continuity correction, 3% of the p-values were less than 0.05. Without the continuity correction, 5% of the p-values were less than 0.05. For the Wald test, 5% of the p-values were less than 0.05. So, all of the tests did a good job limiting significant p-values. So just find out what method is most commonly used in your field. Personally, I'd be more comfortable with a borderline p-value if I knew it passed all of the tests. In summary, an odds ratio is just a ratio of odds. And a log of the odds ratio is just, wait for it, the log of an odds ratio. The odds ratio and the log of the odds ratio tells us if there is a strong or weak relationship between two things, like whether or not having a mutated gene increases the odds of having cancer. And, depending on the field you work in, people use Fisher's exact test, chi-squared, or the Wald test to determine p-values for the significance of that relationship. Hooray! We've made it to the end of another exciting StatQuest. If you like this StatQuest and want to see more of them, please subscribe. And if you want to support StatQuest, well, click the like button below and consider buying one or two of my original songs. All right, until next time, quest on!